Today's notes are going to follow our U-Substitution lesson from last time. We're going to be looking at some advanced integration problems. Some will involve logs, some will involve some trig integration, and we are also going to look at some advanced U-Substitution, some weird cases that can come up in our integration problems. So, our first problem is going to be the integral of x to the fourth minus x minus 4 divided by x squared plus 2 dx. Now, notice that the degree of the numerator is greater than the degree of the denominator. The easiest way to do this problem is going to be starting by doing a division problem. If it was only 1 degree higher, we could use the method of synthetic division, but since it's 2 higher, we're going to have to use polynomial long division, which you learned in Algebra 2 and did again in pre-cal. So I will remind you how that works. Set up our division bar. The numerator goes under the division bar, x to the fourth minus x minus 4. And then the denominator goes right outside, x squared plus 2. And we're going to ask ourselves, what would you multiply the x squared by to give you a result of x to the fourth? That's going to be x squared. X squared times x squared is x to the fourth. And then we multiply x squared also times the plus 2, so that'll give us plus 2x squared. Now we're going to subtract this polynomial from the one that we started with under the division bar. X to the fourth minus x to the fourth is 0. There is no x squared term in this one, so it's 0 minus 2x squared. So that's going to give us a negative 2x squared. And then there's not a linear term here, so it's just going to be bring down the minus x because it's like negative x minus 0. And then also the same with the negative 4, the constant term. Negative 4 minus nothing is negative 4. So now we're going to basically start this process over again. Like this is what we're dividing. So what would you multiply the x squared by to give you a negative 2x squared? That'd be a negative 2. So negative 2 times x squared gives us negative 2x squared. And negative 2 times positive 2 gives us a negative 4. So we are going to subtract this, just like we did before. Negative 2x squared minus negative 2x squared is 0. Negative x minus, we have no linear term here, so it's like 0, gives us negative x. And negative 4 minus negative 4 is negative 4 plus 4, which is 0. Now, as soon as the answer that we have here is of lower degree than the one that we're dividing by, that's when we stop. That's when we're looking at our remainder. This is the remainder. So the way we write the remainder is we go plus this remainder, negative x, over the number that we were dividing by, x squared plus 2. So this is the final answer. So this division problem is equivalent to the answer that we got here. So I'm going to rewrite my integral as the integral of x squared minus 2 plus negative x over x squared plus 2 dx. Okay? Now, this first portion is very easy to integrate. So I'm going to split this into 2 separate integrals. The integral of x squared minus 2 dx, and then plus the integral of negative x over x squared plus 2 dx. So I can handle them independently of each other and just put them together at the end. So let's go ahead and integrate this first one. This is a pretty easy integration problem. The integral of x squared, we add 1 to the power, which would be x cubed, multiply by the reciprocal of the new power, 1/3. And then here we have x to the 0 power, so that'll add 1 to that power and make it x to the first. And then this coefficient -2 is times the reciprocal of 1, which is just 1, so that doesn't change. And I'm not going to put the plus c here because I'm going to have a plus c at the end of integrating this. All of this is still one problem with 1 plus c. All right, so how do we integrate this one? Well, this is a U-substitution problem. Do you recognize it? Our u is the denominator, x squared plus 2. The derivative of u with respect to x is 2x, and I can multiply by the dx on both sides, so du equals 2x dx. I don't have a 2 in the problem already, but I do have an x, so I'm going to multiply by 1/2 to isolate the x dx. Okay, so now I'm going to come back over here and rewrite this integral in terms of the variable u. So what's that going to look like? We're going to have plus the integral. X dx is this part right here, will come out and be replaced with 1/2 du. So we will have just the -1 on top over the u on the bottom, and that x dx comes out and is -1/2 du. So that's what it's going to look like in terms of the variable u. Now this negative times this negative will make a positive, and I can pull that out. Oh, wait a second. I've got the -1 here, and this is a positive 1/2. I apologize. So we are just going to pull the 1/2 out in front, and we can pull the negative out in front. So we're going to go 1/3 x cubed minus 2x minus 1/2 times the integral of 1 over u du. And the integral of 1 over u is one of your note cards. That is the natural log of the absolute value of u. So it's going to be 1/3 x cubed minus 2x minus 1/2 natural log absolute value of u plus c. And now the last step is we're going to take out the u and replace it with what u equaled here. So 1/3 x cubed minus 2x minus 1/2 natural log absolute value x squared plus 2, and then plus c. That's the answer to this problem. All right, let's try another one. Number 2, the integral of x squared in the numerator divided by 5 minus x cubed dx. Okay, so this problem is another U-substitution problem. The degree of the denominator is 1 higher than the degree of the numerator. So we're going to say u is the denominator, 5 minus x cubed, because when I take the derivative of that, I'm going to get an x squared. So du over dx is equal to, the derivative of 5, of course, would be 0, and the derivative of -x cubed is, bring down the 3, -3x, subtract 1 from the power, which is squared. Now I'm going to multiply by dx on both sides, and I'm going to isolate x squared dx. So I'm going to multiply by -1/3 du equals x squared dx. So I'm going to return to my integral problem and rewrite it in terms of the variable u. So I've got the integral of, it's going to be 1 over u. The x squared dx is going to come out and be replaced with the -1/3 du. So now I can pull the -1/3 out in front of my integral symbol, and I'm just integrating 1 over u du, which again is the natural log of the absolute value of u. So -1/3 natural log absolute value of u plus c. And then we're going to take out the u and put it back in with the substitution in terms of the variable x that it's equal to. So it'll be negative 1/3 natural log absolute value of 5 minus x cubed plus c. And that's the answer. That one is done. All right. Next we have problem 3. Problem 3 is the integral of 1 over the square root of 1 minus 16x squared dx. So this one, I hope when you look at it you think, that looks kind of familiar. This 1 over the square root of something minus something with an x squared in it. It looks a whole lot like your note card for the answer to the derivative of the inverse sine. So I'm hoping that that kind of pops off the page at you. Now, when you do the derivative of the inverse sine of x, you get 1 divided by the square root of 1 minus x squared. So this matches, except for we have this 16 in front of it. So I want you to think, this is like there's something substituted in where the x squared was. Can you figure out what that is? Because that is our u. U is equal to 4x here, because if you subbed in the 4x in parentheses and then squared it, you would get 16x squared. So the derivative of u with respect to x is going to equal 4. du equals 4 dx. We don't have an extra 4 in the problem, so 1/4 du is equal to dx. So now I'm going to come back over here and I'm going to say, let's rewrite this as 1 over the square root of 1 minus the quantity u squared. So it's like the 4x was squared, but I'm replacing it with, taking out the 4x and replacing it with u. And then the dx will be replaced with 1/4 du. So the 1/4 can come out in front of the in front of the integral. My goodness. And now what we're left with to integrate is just like our note card for the inverse sine. The answer to the inverse sine derivative. So when we integrate it, we're going to have 1/4 inverse sine of u plus c. And now I'll put the 4x back in place where the u is. And this one is done. All right. So now I have 3 new formulas for you to add to your note card stack that we are going to use for integrals. Actually, I don't quite have room to write this here, so I'm going to go to my next page. So you're going to need to know these and need to know how to use these. So the 3 formulas for inverse trig functions . The first one goes like this. The integral of 1 over the square root of a squared minus u squared du. This looks a whole lot like the inverse sine that we just used in our last example. And that one is actually a special case of this one. So this is going to equal the inverse sine of u, which would be like where the x was in the last one, over a. A is a constant, so if a was 1, like it was in the last problem, u over 1 would just be u. So it's very similar to the one we just used, except for we don't have to have a 1 here now. We could have some other constant value. The next one is the integral of 1 over a squared plus u squared du. And this one is going to equal 1 over a times the inverse tangent of u over a plus c. So again, it was originally 1 over 1 plus x squared, but so now we're going to be able to do it with some other constant value here, not necessarily a 1. If these were 1s, then this would just look like the rule you already used. So that rule that you've already used is a special case of this one. Okay, one last formula to add. The integral of 1 over u times the square root of u squared minus a squared du. And so this is equal to 1 over a inverse secant of the absolute value of u over a plus c. And sometimes you'll see the absolute value bars in front of this u, around this u that is outside the square root in the denominator as well. So again, this is very much like your inverse secant rule that we've used, but it was a 1 here before, and now this could be a 1, but it could be any other constant as well. So let's see how this plays out in a couple of problems as examples. So the next one I'm going to go on to, number 4, looks like this. The integral of 1 over the square root of 4 minus x squared dx. So notice here the a value is going to be the square root of 4. And of course, the square root of 4 is equal to 2. So it's like we're looking at the integral of 1 over the square root of 2 squared minus x squared dx. So this is just going to be the inverse sine of x over 2 plus c, using our new formula right here. Okay? All right, next one, number 5. We have the integral of 1 over 2 plus 9x squared dx. So here, our a value is equal to the square root of 2, okay, which is just going to be the square root of 2 because that's not a nice number like last one was. And also, here, we're going to have a u value equal to 3x, okay? So it's kind of like you're looking at the integral of 1 over the square root of 2 squared plus 3x quantity squared dx. Okay, so we're going to take the derivative of u with respect to the variable x, which is 3, du equals 3 dx, 1/3 du is equal to dx. So we're going to rewrite this in terms of the variable u now. The integral of 1 over the square root of 2 squared plus u squared times 1/3 du. And of course that 1/3 can come out in front of my integral symbol. So now this really just looks like the new formula that I introduced you to today. So we will use this inverse tangent rule, 1 over a times the inverse tangent of u over a plus c. So this is going to be 1/3 out in front times 1 over a, our a value is the square root of 2, times the inverse tangent of u over a plus c. And of course we can take the u out and replace it with the 3x. So 1/3 times 1 over the square root of 2 inverse tangent of 3x over the square root of 2 plus c. And no, you do not need to rationalize those square roots in the denominators. You can leave them just like that. All right. So we did one with the inverse sine and one with the inverse tangent. I bet you'll never guess what the next example is going to be with. I wonder. Number 6, the integral of 1 over x times the square root of 4x squared minus 9 dx. So, what does this look like? The inverse secant one that I just shared with you. Absolutely. So, let's think about this. This would be like 1 over x times the square root of, this is a 2x quantity squared minus a 3 squared dx. Now, it looks like our u value would be equal to 2x and our a value would be equal to 3. But we have a problem here. Have you noticed, let me put this other one back. When we had the inverse secant one before, u is out front and u is squared. These are the same thing. These are supposed to match, and right here I have a 2x, but over here I have an x. These are supposed to match, and they do not. So what are we going to do about this? This is a problem. Well, we sometimes have to be creative and do clever little things in math to make things work out the way we want them to. And one of those special little techniques we can use is multiplying by a clever form of the number 1. Okay, so if I multiply by 2 over 2, I can force there to be a 2 out here with my x in the denominator like I need in order to use this new rule that I have. And that's no big deal at all, because I can always pull the 2 from the numerator out in front of the integral symbol, and all is well. So let's see. If our u is equal to 2x, then our du dx is equal to 2. And I can multiply by dx on both sides. And oh, wait a minute, a 2 dx, multiplying by that 2 over 2 actually gave me the 2 that I was going to come up with right here anyway. So I really don't even need to pull it out, because I can take that 2 with the dx and just replace it with a du. So what is this going to look like? See, it'll be 2 over 2x square root of 2x quantity squared minus 3 squared dx. So this 2 and this dx can come out and be replaced with the du. So now I've got 1 over u square root of u squared minus 3 squared du in terms of the variable u. So now we're going to use our new formula, 1 over u, which is 1 over a, which is 3, times the inverse secant of the absolute value of u over a plus c. And of course, we'll throw that 2x back in place of the u so that our answer is in terms of the variable x. And this one is now finished. Okay. Number 7. We're going to try a new technique on number 7. Kind of an interesting approach. We're going to rewrite an integrand as the sum, of two quotients. Lots of good math vocabulary in that directive. Okay, so this is what the problem is. The integral of x plus 2 over the square root of 4 minus x squared dx. So what's the big deal with this problem? What makes this different from any of the others we've done? Well, we've done problems with a denominator like this with just the x on top. When just that x is on top, we go, oh, I think that the stuff under the root should be a u. And the derivative of u is 2x, so there's an x on top. This looks like a u-sub problem. We've also done problems that look like this, where we see the constant on top and the square root of 4 minus x squared on the bottom. That sure looks a lot like the inverse sine derivative. So integrating that would yield the inverse sine function. But what do you do if you've got both of them together? We haven't really seen one like that before, and that actually, as it turns out, is not a good situation. So that's why we're going to rewrite it as a sum of two quotients. It's kind of like if you had the common denominator here and you added the numerators. We're kind of going to back up and go backwards on that step and split it into two separate fractions. So we'll have x over the square root of 4 minus x squared dx plus the integral of 2 over the square root of 4 minus x squared dx. So now it's like two problems for the price of one. We're going to handle each one of these independently of the other. So on this one, it's a U-substitution, where u is equal to 4 minus x squared. So we'll take the derivative of u with respect to x and get negative 2x, and then multiply by the dx on both sides. And then we're going to say no negative 2 already here, so let's multiply by negative 1/2 to isolate x dx. I do have the x dx, so that will come out and be replaced with a negative 1/2 du. So now I have the integral of 1 over the square root of u times negative 1/2 du. And the negative 1/2 can come out in front, and then I'm going to integrate u to the negative 1/2 power du. So I'll be able to use the power rule backwards. So add 1 to my power, that's going to be u to the positive 1/2, multiply by the reciprocal of my new power, so that's 2, and that does multiply by the negative 1/2 I already had. And then we would have the plus c, but remember this is all together as one integral, so I'm just going to put 1 plus c at the very end. So now I have 1/2 times 2, which is 1, and the negative, and this 1/2 power is the square root of u. And I'm going to go back and replace u with 4 minus x squared, so negative square root of 4 minus x squared. So that's the first part of the problem. And now we're going to come over here and tackle this one. So take a look over here. It looks like the inverse sine derivative, except for it's got this extra constant here. So let's think of that as an a value of 2. And this 2 on the top probably better come out in front of the integral. So we'll go plus 2 times the integral of 1 over the square root of 2 squared minus x squared dx. So this will be plus 2 times, we can do the inverse sine of x over 2 plus c. And now notice I have some equivalent statement on every line until I get down here, and then I've got 3 that don't have the rest. Even though this is kind of done, I need to make every line equivalent to the line above it. I know it seems tedious, but if this is a free response problem on the AP exam, you get in trouble if you say something follows that is not actually equivalent to what was above. So we want each line to show an equal expression to the one that preceded it. Okay, technical math, important stuff. Okay, Well, we have one more advanced problem to do together today, and it's a super fun one because you're going to get to go travel a little bit back in time to something you learned a while back, which is called completing the square. Do you remember completing the square? Does it bring back fond memories from the past? I hope so. So we're going to complete the square to integrate. And by the way, it's okay if it doesn't because I'm going to remind you how to do this. So problem number 8, we're going to do the integral of 1 over x squared minus 4x plus 7 dx. So I want you to look at this denominator. It's a quadratic equation, okay? And I want you to consider if the denominator was a sum of two squares, it would match the inverse tangent pattern for that formula that we looked at earlier. So I'm just going to force it to be the sum of two squares by completing the square, okay? So if you'll remember, whenever you completed the square, there was a special number you had to add into the problem. That number was half of the b value, which was the coefficient of your linear term, the one with just an x on it, squared. But you can't just go around adding a random number into a problem and maintain equality, can you? So the technique that you're going to use is you are going to add and subtract. Just add it and then subtract it. Why not? If you add it and then you subtract it back away, it maintains equality. So our b value is 4. So I want you, that's your coefficient of your linear term here in the denominator. So if you take 4 and divide it by 2, you get 2. And then if you square it, 2 squared is 4. So the 4 is the magical special number that we're going to add and subtract into the problem, okay? So I'm going to do this kind of elaborately so that it's really clear. We're going to have x squared minus 4x, and then I'm going to add this special number, half of 4, which is 2, squared is 4, so I'm going to add a 4 right here. I just completed the square here. This is now the square of a binomial, okay? We'll look at that in just a moment. But I can't just add the 4, I also have to subtract the 4. So I'm going to put minus 4 right over here with the plus 7. So that's kind of hanging out on the end, on the fringe. So now I've got the ability to rewrite this as the square of a binomial. Square root of the first term, x, sine of the middle term, minus square root of the third term, 4, which is 2. So this is now the quantity x minus 2 squared. If I was to multiply x minus 2 times x minus 2 and FOIL it out, I get x squared minus 4x plus 4. So I have just completed the square here to be able to rewrite this as the square of a binomial. And then I'm going to go ahead and put these two together now. Negative 4 plus 7 is, of course, 3. How did that help me? Well, now I can think of this 3 as that constant number, well, the square root of 3 as the a value. And I can think of the stuff that's squared here with the x in it as my u value. U would equal x minus 2 in this case. So it's like I've rewritten it as 1 over u squared plus the square root of 3 squared. But now I need to get this dx in terms of u. So du dx equals 1. Du is just equal to dx. I don't have to multiply by any special numbers. So I'm just going to take out the dx and replace it with a du. So now I can use the inverse tangent formula that we got just today in class. So we're going to write this integral as the answer being 1 over the square root of 3, that's our a value, times the inverse tangent of, normally it's x on top, but we're taking our u on top of a, the square root of 3, and then plus c. And now I'm going to take out that u and replace it with the expression in terms of the variable x. So the inverse tangent of x minus 2 over the square root of 3 plus c. Look at that. What an amazing answer to an integration problem. Y'all are doing some advanced integration techniques now. I hope you feel super smart, because you are. Absolutely. Now, are you going to see a whole bunch of these completing the square integration problems pop up? Probably not. It's probably rare that you would see one come up like this. But I just want to make sure that you are prepared for anything and everything that they could throw your way on the AP exam. So even though that you don't see these too often, I definitely want you to know how to tackle a problem like this. So I wish you all the best of luck on your homework. Some of them are a little bit challenging, but you should have an example problem to guide you through everything you're going to find. Feel free to buddy up with a partner from class if you want to discuss it and work some out in partners or small groups, or definitely send me an email or let me know if you need any help at all. So have an absolutely wonderful day, and I look forward to meeting with you again soon. Bye-bye.